Hi, my name is Patrick Ang, and I'm the instructor for Rock the Diploma's online Chemistry 30 Diploma Prep course. First of all, thank you very much for choosing RTD for your Diploma Prep, and I really hope you guys enjoy this class. This is something I always look forward to every year when Diploma Prep rolls around. I really look forward to teaching this class. Just to give you a little bit of my background, I've been the RTD online chemistry instructor for close to a decade now. And once upon a time, I was in a graduate program in organic chemistry, and I've been tutoring and teaching chemistry for close to 20 years. So as you can see, it's probably apparent that I totally love chemistry, and I hope this comes out in my teaching. A little bit more about myself. In my spare time, I like to play guitar and also a little bit of softball. Anyway, before we talk about our introductory unit, which is Thermochemical Changes, we should probably talk a little bit about what this diploma exam entails. The Chemistry 30 Diploma exam consists of 44 multiple choice and 16 numerical response items of equal weight. What this means is that your exam is going to be fully machine scored. You're going to be filling out a bubble sheet. Now, something cool that happened over the past few years is that the amount of time they give you to do this exam has been extended considerably. You guys have 6 hours. 6 hours to complete this exam, which is awesome. Which means that you can take your time with each question. Make sure that what you're answering is correct. Making sure that you're filling out your bubbles properly, and also that the bubbles that you fill out line up with the questions with which they go. Now, this class consists of 4 different units. We have thermochemistry, and on the exam, this is going to be between 12 and 13 questions. Electrochemistry, which can be between 17 and 19 questions. Organic chemistry, which is between 11 and 12 questions. And another big unit, just like electrochemistry, chemical equilibrium along with acid-base. This is another one where you can expect between 17 and 19 questions. Now, something I wanted to bring up is that you can go to this website, www.rtdlearning.com, for select solutions to the practice questions contained within. In the back of your booklets are a whole bunch of practice questions that are an awful lot like the questions you will see on your diploma exam. A while back, I made a set of solutions to those, well, not all the questions in the back, but to the ones that I thought were the most important, the ones that I thought were kind of the more challenging ones. The questions don't exactly line up. We've had questions added and some removed, but rest assured, when you look at the solutions, it's fairly easy to see which questions they go with. They're fairly close. The question number is fairly close to where they were if they had changed. There's also an additional downloadable extra practice booklet if you want to be a little bit more ambitious and do more questions for practice. All right, so let's talk about thermochemical changes. Thermochemical changes involve changes in the potential energy of a particular chemical system or reaction. And in this course, we refer to these generally as the enthalpy change, or delta H, for that chemical reaction, and how these changes in potential energy change the kinetic energy of the surroundings of that chemical system. And we refer to this quantity, this change in kinetic energy, as Q. Now, to calculate Q for the surroundings of a chemical system, we use this formula, which I'm sure you've seen before. It is mc delta T, where m refers to the mass of those surroundings, and C refers to the specific heat capacity of the substance of those surroundings, and delta T refers to the change in temperature. Now, the way delta H is related to this Q, so the delta H of the system is simply equal to the negative Q, or the opposite sign of that Q value. And of course, there's a relationship between the delta H for a particular chemical reaction and the number of moles of chemicals that are reacting, and what we refer to as the delta H subscript M, or the molar enthalpy. This is the molar enthalpy for that particular chemical reaction. So over back on the kinetic energy side, generally associated with the surroundings of a chemical system, there will be a temperature change. Okay, there's a temperature change. that occurs because the surroundings either get heated or lose thermal energy. And of course, heat refers to the transfer of thermal energy from the chemical system to the surroundings. Now, really, it's all about the interplay between how the potential energy change affects the kinetic energy change. And on the potential side, changes in potential energy can either happen through intermolecular interactions. Okay, over on this side here, we're talking about things such as boiling, melting, etc. Okay, basically changes in state. Lucky for you guys, this is not going to be covered on your diploma exam. You guys have probably heard about things like the latent heat of fusion and the latent heat of vaporization. We don't cover those things on the diploma exam. Really, when we're talking about changes in potential energy, we're talking about intramolecular changes. So in fact, actually, there's more focus over here on this side. Okay, this is what your diploma exam is going to be focused on. Okay, so your diploma is going to be focusing on those. So with intramolecular changes and the potential energy changes associated with that comes chemical change. And it is these sorts of processes where we'll be looking at how the change of potential energy happens. And of course, we're talking about chemical reactions and also dissociation processes, where let's say if we take an ionic compound and dissolve these in water, and is there a change in potential energy associated with that? Now, for a change in potential energy, we can either have an endothermic process or an exothermic process. Okay, the endothermic process, this refers to a scenario where the delta H for that particular chemical reaction is positive. And for an exothermic process, the delta H would be negative. For an endothermic chemical reaction, it is because there's a gain in potential energy. And that's why the delta H is positive. And for an exothermic reaction, there's a release of potential energy. And that's why the delta H is negative. Now what we have is these diagrams over here and here. These are examples of what we refer to as calorimetry experiments. Let's take a look over here on the endothermic side over here. We have ourselves a chemical system, and in this particular scenario, this is an exothermic process, and what's happening is that the chemical system is releasing potential energy into the surroundings. In this case, it's water that serves as the surroundings of our chemical system, and because of the release of potential energy, there's a transfer of thermal energy to the water, and what we see that the temperature of the water increases. Around this experiment, what we have is we have some insulation, and that keeps the energy transfer strictly between the chemical system and the water that surrounds it. Okay, and of course on the endothermic side, what happens is that there's a gain in potential energy by the chemical system, and this is because it is now getting thermal energy from the surroundings, and what we would observe is we would observe a decrease in temperature in the surroundings due to the chemical system taking in thermal energy, increasing its potential energy in an endothermic process. Now, some definitions that you're going to have to know of with regards to heat transfer and calorimetry. Right, you have to know what thermal energy is. Okay, thermal energy is the kinetic energy of the entities of a substance, and thermal energy basically increases with temperature. There's this formula here, which I've spoken about already. Okay, Q is equal to mc delta T, and it is important to remember that this is only for the kinetic energy changes of the surroundings. Now, just a little bit more information on this value C here. This is what we refer to as the specific heat capacity of the substance that serves as the surroundings for our chemical system. And if we look at the data booklet that we're allowed to use for the exam, this is a series of specific heat capacities 298.15 Kelvin and 100 kilopascals. And the main specific heat capacity that you will be concerned with is the specific heat capacity of water, which is 4.19 joules per gram degree Celsius. Okay, you're going to see this an awful lot with the calculations that we do and also in a lot of the example questions at the back of the booklet. Now, don't forget that we have to be aware of our Q value, which is calculated with this formula here, versus the delta H for the reaction, which I refer to as the enthalpy change for a particular chemical reaction, which is, of course, in general, the change in potential energy of a chemical reaction. And the relationship between the Q that we would measure, so the Q for the surroundings, is equal to the opposite sign of the delta H value for the system. Okay, temperature, what temperature is? Temperature is a measure of the average kinetic energy of the entities of a substance. Heat is the thermal energy transferred between systems, and heat is not possessed by a system. In fact, actually, in proper scientific terminology, heat is the verb, so you heat something. Thermal energy is the noun. You heat something and you are transferring thermal energy to that thing. We also have chemical potential energy, okay, and this is the energy stored in chemical bonds. And of course, enthalpy, which is the total kinetic and potential energy in a chemical system. And the change in enthalpy is the difference in enthalpy, and we assume the difference in chemical potential energy. Like I said before, in general, we think of an enthalpy change as the change in potential energy. It's the difference in chemical potential energy between the products and the reactants. And it's important to note that the temperature of the system does not change. Okay, so the temperature of a chemical system does not change. It is strictly just the change in potential energy, and we associate temperature changes with the surroundings, like what we see here in this formula for Q. Now, in general, the enthalpy change for a chemical reaction is the enthalpy of the products minus the enthalpy of the reactants. And of course, we have this quantity here, which is the molar change in enthalpy. Okay, the molar change in enthalpy, and it's the change in energy per mole of a substance undergoing a specific reaction. We have this formula here. This is also going to be another important formula. And something I want you guys to note is that this delta H, we have to remember that we tend to use this only for potential energy changes of chemical reactions. That's my abbreviation there for chemical reactions. This quantity here, molar enthalpy change, I should say, sorry, molar enthalpy change. This is going to be an important quantity to note. This quantity is measured in kilojoules per mole. Kilojoules per mole. This is the standard unit for molar enthalpy. And really, when we do these sorts of calculations, what it essentially is, it is an energy stoichiometry calculation. And I'm just going to abbreviate stoichiometry here, STOIC. It's an energy stoichiometry calculation. It's kind of like what we see in Chem 20. If you notice, we have various subscripts. Over here, for example, after the delta, we have this letter R. And in this table here, we list off what the various subscripts mean. So if an R is placed after the delta, what we're talking about is we're talking about any reaction specified. If it was a combustion, we would use C. If it was a formation, we'd use F. If it was a decomposition, we'd use D. And if it's a dissolving process or a solution process, we'd use SOL. And if it was some kind of dilution, we'd use DIL. And of course, don't forget that what this M means, this M is referring to molar. So what we have here on the left is a diagram that shows the relationship between the change in potential energy of a chemical system and the change in kinetic energy of the surroundings of that system. We can see here for this particular reaction between zinc and HCl that there's a decrease in potential energy. And if you recall, what I'd said before was that here in this case, this delta H would be negative because of that decrease in potential energy. Notice how for the kinetic energy of the surroundings, there is an increase in kinetic energy for the surroundings. And this increase is equal in magnitude to the delta H, but it goes in the opposite direction. Our Q here is positive. And so this kind of goes with what I was saying before about how the way Q and delta H are related is that the Q for a particular surrounding is equal to the opposite sign version of that delta H for reaction. Okay, so equal in magnitude, opposite in sign. This diagram over here on the right is just a reminder of how a calorimetry setup works, that here in this exothermic process, for example, thermal energy could be transferred to the surroundings, or the thermal energy could be taken from the surroundings, which would increase the potential energy of the chemical system. We have insulation around everything so that the energy exchange strictly happens between the chemical system and the water surroundings. So we get this relationship where Q and delta H are equal in magnitude yet opposite in sign. Let's take a look at how we calculate these various quantities that we've been talking about. In this first example, methylpropane, or C4H10, is used as a lighter fluid. When 1.80 grams of methylpropane is burned in a calorimeter, the temperature of 2.60 grams of water changed from 20 degrees Celsius to 29.7 degrees Celsius. In the first part, we want to calculate the amount of thermal energy absorbed by the water. Now recall, because we're calculating thermal energy, and in this case we're dealing with the thermal energy absorbed by water, remember that water is what is serving as the surroundings for our chemical reaction. Water is the surroundings. So what we're going to be calculating is we're going to be calculating a Q. We know that to calculate a Q, what it equals the mass of our water surroundings times the specific heat capacity of water times whatever the change in temperature, or delta T. For the specific heat capacity of water from our data book, we know it's 4.19 joules per gram degree Celsius. And I want to talk a little bit about the units of this particular number. So according to our data booklet, once again, the C for H2O is equal to 4.19 joules per gram degree Celsius. I want to actually use a unit that looks an awful lot like this but is not stated in the exact way. I want to use these units. Kilojoules per kilogram degree Celsius. These are in fact the same units as what you see there. We have kilojoules over kilogram. So what actually happens, it's like times 1000 on top and times 1000 on the bottom. So these K's could cancel, leaving behind the same units that we see in the data booklet. But in fact, actually, I want to use these particular units, and there's a reason why. The reason for that is because what we're going to end up with is we're going to end up with a Q value that will be measured in kilojoules. And remember how I talked about the units of molar enthalpy changes in kilojoules per mole. So ideally we want our Q value to be in kilojoules so that can translate to whatever the enthalpy change value comes out to for this particular reaction. And if you notice how our mass of water is given in kilograms. So we have 2.60 kilograms of water, and in the bottom of these units, for these kilograms here, these are the units for our mass of water in the surroundings. Okay, so here's the idea that we're going to use these units of kilojoules per kilogram degree Celsius. Okay, and the reason why is because, well, if we have a mass of water in kilograms, let's actually put all these values into our formula. So our mass of water is 2.60 kilograms. That's our mass of water. If we take a look at our specific heat capacity for water, 4.19 kilojoules per kilogram degree Celsius. And of course, here we have two different temperatures. We have an initial temperature, which is 20 degrees Celsius. We have a final temperature, which is 29.7 degrees Celsius. Don't forget that the way we calculate our delta T is our delta T is equal to our final temperature minus our initial temperature, and in this case it is 29.7 degrees Celsius minus 20.0, which gives us 9.7 degrees Celsius. Okay, so that's what goes in for delta T, 9.7 degrees Celsius. And if you look at how the units work here, the kilograms associated with the mass of water will cancel with the kilograms here in these units for our specific heat capacity, and of course the degrees Celsius will cancel as well, leaving behind a Q value that will be measured in kilojoules, which is actually what we want. With all of the values being given to 3 significant digits, we should report a Q value in 3 significant digits, and this Q value is positive 106. Okay, when you punch this into your calculator, you get this. And don't forget, of course, you don't put the units in. But there's the value. If we round it correctly, we get this value in 3 significant digits, positive 106 kilojoules. All right, now we want to determine the enthalpy change for this combustion of 1.8 grams or 1.80 grams of methylpropane. So here in this scenario, our delta H for combustion is going to be equal to negative 106 kilojoules. Okay, remember that the delta H for a particular reaction is simply opposite in sign to what we see for Q. In this case, Q is positive, so our delta H is going to have the same number, but it's going to be negative. Okay, so don't forget that here this is opposite in sign to Q. Okay, but also equal in magnitude. Now finally, we're going to determine the molar enthalpy of combustion for methylpropane. And remember that when we are dealing with the molar enthalpy for the combustion of methylpropane, or molar enthalpies in general, that when we say molar enthalpy, this is associated. It's associated with 1 mole of methylpropane, or C4H10. And also recall that we have this formula where if we have the delta H for a reaction, what it's equal to the number of moles times the molar enthalpy for that reaction. If we rearrange this formula, remember this is what we're trying to figure out. If we were to rearrange this formula, it would be that the molar enthalpy would simply be equal to the delta H for that reaction over the number of moles. Well, we already have the delta H for this reaction, but now we need to figure out the number of moles of the compound in question. Now don't forget, this 1.80 grams is the mass of our compound. If you recall, the way we would calculate the moles of this substance is we would take the mass of our substance, in this case it's 1.80 grams, and we simply divide that by the molar mass of this substance, which is 58.14 grams. Okay, so we have 1 mole for every 58.14 grams. Okay, so we're dividing the mass by the molar mass of that substance, and of course, the way we're showing it, these gram units will cancel, and what it would give us this. This many moles of C4H10. Now finally, to finish this off, and here's where I got some room, right over this calculator diagram, that to calculate the molar enthalpy for combustion, it is equal to the delta H that we see up there, divide that by the number of moles, and what it equals is, and here I'm going to actually use this value, because remember that for intermediate calculations en route to a final answer, we should use the unrounded version, just like how I'm taking, as many decimals as sensible over here. It's going to be negative 105.6718. And this is, of course, divided by and this is in kilojoules, sorry, and this is, of course, divided by our 0.030960 moles. And now finally, we can report our final answer in 3 significant digits, which is negative 3.42 times 10 to the 3 kilojoules per mole. Okay, and remember how I said that kilojoules per mole are the standard unit for the molar enthalpy of a particular reactant. Notice how we have kilojoules on top divided by moles on the bottom, and this, obviously comes from the moles of our substance, right? Our final answer is negative 3.42 times 10 to the 3 kilojoules per mole, with an answer, of course, in 3 significant digits, as we expect. From the last example, hopefully it's apparent that there are certain data values that go with either the surroundings of our chemical system or the system itself. Don't forget that with our surroundings, what we're calculating is we're calculating a Q, and with our system, we are calculating a delta H. And of course, the way Q and delta H are related is that Q is equal to the opposite sign number of whatever the delta H is. Now, associated with our surroundings, what we will have is we will have a mass of water. And don't forget that I said that ideally we want to have our mass of water in kilograms, because when we have our specific heat capacity of water, which of course is equal to 4.19 from our data booklet, we want to use these units of kilojoules per kilogram degrees Celsius. That is because when we eventually calculate our Q, we want it to be in kilojoules, because this translates well to the units of kilojoules per mole, which are the standard units of molar enthalpy change. And of course, there is also a delta T, or a change in temperature, and the way we calculate this is by taking our final temperature and from it subtracting our initial temperature, and of course this is going to be measured in degrees Celsius. With our system, what we have is we have the delta H for that reaction. Just like Q, we want this to be measured in kilojoules. We also have a molar delta H, whose standard units are kilojoules per mole. Because the chemical system is, dealing with the stuff that's actually reacting associated with it, and what links the delta H and also the molar enthalpy change is the number of moles of our reactant, which of course, this is measured in moles. If we have a mass of reactant, the mass of the reactant, not to be confused with the mass of H2O, the mass of the reactant ought to be measured in grams, and of course, don't forget that how these two things are linked. We link these using the molar mass of our reactants, which of course is measured in grams per mole. Okay, so I think what I wanted to state here is that our mass of our water surroundings, these are measured in kilograms, whereas the mass of a particular reactant, if given in a question, this ought to be measured in grams, because we can calculate the number of moles of that reactant using the molar mass, which is measured in grams per mole. So this example number 2 is actually a little bit more tricky than the previous example. Here in this case, we got a lot of things going on in this question. In fact, actually, what I recommend you do before any example that I present in this recording is maybe pause the recording and try it on your own. Try it on your own, and then you can unpause it, and then you'll see me write out the solution for this. All right, so in this particular example, a student is asked to prepare a 50 ml solution of ammonium nitrate. Remember that ammonium nitrate, its formula is NH4NO3. Okay, that's ammonium nitrate. If the molar enthalpy of solution of ammonium nitrate is positive 25.0 kilojoules per mole, we're going to determine the mass of ammonium nitrate that should be dissolved to decrease the temperature of the water by 7.55 degrees Celsius. You see what I mean? A lot of stuff going on. Now, from the previous slide, I talked about how the different data values can be broken up into either being part of the surroundings or part of the system. And so in fact, actually, that's what we're going to do. We're going to divide up the data values as either part of the surroundings or the system. Okay, in this first little bit where they say that the student is asked to prepare a 50 ml solution of ammonium nitrate. Okay, so we have ourselves a 50 ml solution. Okay, so there we go, a 50 ml solution. This is actually from where we're going to get the mass of H2O. The reason why is because for a particular aqueous solution, we can assume that the density of water is equal to the density of the solution. And if you recall, the density of water is 1.00 grams per milliliter. Okay, so we assume that the density of the solution is going to be the same as the density of water. So knowing that, the fact that it's a 50 ml solution, we know that the mass of H2O in this case, because the density is 1 gram per milliliter, the mass of H2O is going to be 50.0 grams. If you recall what I said from the previous slide, that ideally you want your mass of water surroundings to be in kilograms. So I'm simply going to take that 50 and divide it by 1,000, and what I get is 0.0500 kilograms of water. Okay, let's read on. So there we go. Our first data value goes under the surroundings heading. Now, if the molar enthalpy of solution of ammonium nitrate is positive 25.0 kilojoules per mole, this is something that goes under the system heading. This is a molar enthalpy of solution. This goes under our system heading. Okay, we're talking about the ammonium nitrate. This is the stuff that's dissolving. This is what goes in the system. And this here's the molar enthalpy. Positive 25.0 kilojoules per mole. Now what we want to do is we want to determine the mass of ammonium nitrate. Okay, so here we're talking about, once again, the chemical itself that's dissolving. So this is going to go under the system heading. Here in this case, we are looking for the mass of ammonium nitrate. That goes into the system heading, and this is what we're determining. That should be dissolved to decrease the temperature. So we're going to be decreasing the temperature by 7.55 degrees Celsius. Okay, so here they actually give us our delta T. This is our delta T. And we are decreasing the temperature, so that means that our delta T is going to be negative. Okay, so this is going to go under the surroundings heading. So our delta T is going to equal negative 7.55 degrees Celsius. Okay, if you recall, don't forget that we also have a specific heat capacity of water that's going to go under our surroundings heading. And that's going to be 4.19 according to our data book, but we're going to use these units of kilojoules per kilogram degrees Celsius. Okay, so knowing what information we have, now that we've slotted all the data values underneath, whether they be with the surroundings or with the system, with all the stuff that we have in the surroundings, we can see that we can easily calculate a Q from all this information. Okay, so let's go ahead and calculate the Q. So that's the idea, that if we separate out our data values into whether they go with the surroundings or with the system, it ought to be easy to see what we can calculate easily. So we can calculate a Q, and we know that our Q is going to equal the mass of H2O times the specific heat capacity of H2O times delta T. All right, let's punch those values in. Remember that our mass of H2O is going to be in kilograms. And remember that when you guys are writing out these things on your exam, you don't necessarily have to put the units down, but I'm just putting the units down to show you how the units work, and we end up with a Q in kilojoules, as I mentioned before. But as long as you know that your mass of water for the surroundings is in kilograms, and you're using these units for C, where it's 4.19 kilojoules per kilogram degrees Celsius, and of course our delta T is going to be negative 7.55 degrees Celsius, we can see that the units are going to cancel as such, leaving behind our desired units of kilojoules for our Q. When we punch all these into our calculator, we're going to get a Q of negative 1.581725 kilojoules. Now this is an intermediate calculation. This isn't our final answer. And if you notice, I put a lot of decimals here. And so whenever we calculate an intermediate calculation, what I recommend, and let me just write this out here. I've said this before, that you want to keep as many decimals as sensible for your intermediate calculations. Okay, because once we get that, we can now go over to the system heading, and we know that we have our Q. We can easily calculate our plain old delta H for solution for this particular scenario. It's simply going to be the opposite sign version of our Q value. So it's going to be positive 1.581725. Okay, now that we have that, we're looking for the mass of NH4NO3. we know that given our molar enthalpy and also our enthalpy change for the specific reaction, we can easily determine the moles of NH4NO3 from the molar enthalpy formula, where it's going to be the plain old delta H divided by the molar enthalpy of solution. And what this is going to equal is this. Okay, there we go. And when we do this calculation, this is what we're going to get. 0.063269. Once again, this is an intermediate calculation. I'm going to keep as many decimals as sensible. And now finally, we're going to determine our mass of ammonium nitrate. Okay, we're simply going to take our moles of NH4NO3 and multiply it by the molar mass of NH4NO3. This is going to be 0.063269 moles times. Okay, and the molar mass of ammonium nitrate is 80.06 grams per mole. And what that's going to equal is about 5.07 grams. Okay, and there's our final answer. A couple of things to note. This answer, I've rounded this answer to 3 sig digs, which is what it ought to be rounded to, given the sig digs, all of our information is given in. Don't forget that for your diploma, all right, the answers that you give are going to be, they have to be to the correct number of sig digs, okay? And you also have to not forget to round correctly. Don't forget your rules of rounding. All right, and the reason why this answer actually works, in fact, actually, this is something you're going to see more often than not. If you look at the answer that we have an answer of 5.07. On your bubble sheet, you're going to have 4 bubbles to put in numerical response answers. So let's say if we have 4 bubbles here, you would fill in your bubbles as such. There would be a 5 here, there would be a decimal in the next bubble, and also a 0, and then finally a 7 here. Okay, and you can see that this answer fits into 4 bubbles quite nicely. Now, another one of the nice things that they've been doing on diploma exams over the past few years is that they've specified how many decimal places they want you to round your answer to. So, for example, for this one, they would say round your answer to 2 decimal places. And as you can see, that the correct answer fits into the 4 bubbles set up nicely. Now, let's say if by some chance, although this is rare, let's say if by some chance the correct answer ought to be recorded in only the first 3 bubbles, it's an important thing to remember that when you fill in your numerical response, okay, if there are 4 bubbles this way, you have to start your entry starting at the far left. And if it was, let's say, fill in only 3 of the 4 bubbles, these would be the ones that you would fill in, and then you'd leave this one blank. Okay? But in chemistry, it's very rare. Pretty much all your answers are going to fit into the 4 bubbles quite nicely, like this answer that we have here, 5.07. So example 3, if you guys like, you can go ahead and pause this recording and try this question on your own, and resume the recording if you want to see how it's taken up. So what makes this question tricky? Let's draw out what's going on. What we have is a 150 ml solution of HCl, and it is being mixed with a 150 ml solution of NaOH. Okay, so 150 mils of a 0.200 mole per liter HCl is added to 150 mils of 0.200 mole per liter NaOH. If the initial temperature of both solutions is 25 degrees Celsius and the final temperature of the mixture after the reaction was complete was 27.1 degrees Celsius, determine the molar enthalpy of neutralization for HCl. So we're mixing these two 150 ml solutions together, and what happens is we're going to get a combined solution with a larger volume of 300 milliliters. And it is in this vessel, this is where the reaction takes place. It takes place in this larger volume, which means that, let's say if we were to determine the mass of water for the surroundings of our chemical system, we're going to have to use a combined volume of both the HCl solution and the NaOH solution, 300 milliliters. So just like before, what we're going to do is we're going to organize our solution under a surroundings heading and a system heading. All right, so we just talked about how the mass of H2O, and this goes under our surroundings heading, is going to be the combined volume of these two solutions. So our mass of H2O is going to be 300 grams. And of course, we want our mass of H2O in kilograms, so it's going to be 0.300 kilograms. Right? And don't forget that this is a combined, it's a combined mass from those two solutions. Right? So they give us an initial temperature. So this here is an initial temperature, the 25.0 degrees Celsius, and this is our final temperature, so we can easily calculate a delta T for this reaction. It's going to be the final temperature, which is 27.1 degrees Celsius minus the initial temperature of 25.0 degrees Celsius, which of course is going to equal 2.1 degrees Celsius. And under the surroundings heading, we of course have our specific heat capacity, which is 4.19 kilojoules per kilogram degree Celsius. Now, as the last point, they want us to determine the molar enthalpy of neutralization for HCl. This molar enthalpy goes under the system heading. Okay, and this is what we're trying to determine. Right, so it's easy to see that given the data that we have under the surroundings heading, we can easily calculate a Q. So our Q is going to be the mass of H2O times the specific heat capacity of H2O times our delta T. With our mass of H2O in kilograms, we're using these special units of kilojoules per kilogram degree Celsius for the specific heat capacity and our change in temperature in degrees Celsius. We know that our units are good. We don't need to write them down when we're working out this calculation on our exam. I know that I'm going to get an answer for Q, or a result for Q, in kilojoules. So positive 2.6397 kilojoules. With this value for Q, we could determine the delta H for neutralization for this specific situation. For HCl, okay, and it's going to equal the negative version of that number. Right now we can start working towards determining the molar enthalpy for neutralization. What we need for this is we're going to need the moles of HCl in order to determine this, and it's HCl specifically. If we look back at the question, we have a volume of an HCl solution and also the concentration of the HCl solution. So really, it's only these data values that we're going to use to determine our moles of HCl. Don't forget that in order to calculate the moles from a concentration and a volume, it is the concentration of the HCl solution times its volume. And what this equals, it equals the concentration of 0.200 moles per liter times, and remember here we have to use the liter volume of this HCl solution, so it's going to be 0.150 liters. Don't forget the reason why that is because we want these liter units to cancel out, leaving behind a value in moles. Okay, so don't forget, we only want to use the volume of the HCl solution. When we do that calculation, what we're going to get is we're going to get 0.0300 moles of HCl. And now that we have the moles of HCl, we can easily calculate the molar enthalpy of neutralization. Okay, it's going to equal that delta H over the moles. So it's negative 2.6397 kilojoules over the number of moles, which is 0.0300. And what we get as our final answer is negative 88.0 kilojoules per mole, correctly rounded to 3 sig digs, as expected. So what I'm going to do here is I'm going to basically explain what it means to perform a calorimetry experiment and also summarize basically what it is, like what the point of all of this is. So I'm going to go ahead and I'm going to draw the apparatus. For this red rectangle, what I'm drawing is I'm drawing our chemical system. And of course, what we do is we surround the chemical system, usually with water. It's a water surrounding. And of course, we're going to need some insulation. Okay, so we got ourselves some insulation, which will keep the energy transfer strictly between the chemical system and the surroundings. Into the surroundings, what I'm going to place is I'm going to place a thermometer, and the thermometer is going to be the indicator of temperature changes. Okay, so the first thing is that here we have ourselves a chemical system. The question we ask ourselves is this. This is really what it is we're trying to determine in a calorimetry experiment. Let me just write this out. Okay, the question is, how does the potential energy change in a reaction? And of course, the kind of value we're looking for in this case is we're looking for the delta H for the reaction, okay, which is going to be measured in kilojoules. Now, the thing is, don't forget what we have around that chemical system are H2O surroundings. Basically, it is the delta T is the indicator for the change in potential energy. All right, we have ourselves a delta T, which is equal to the final temperature minus the initial temperature. We also have a mass of H2O, which I recommended to be in kilograms. And also we have our specific heat capacity of water, which is 4.19 kilojoules per kilogram degrees Celsius. From all this information, we can calculate a Q, which has that MC delta T formula, okay, which will give us a final result in kilojoules, right? And once we get this, what this tells us how the kinetic energy of H2O changes as a result of delta H. Of course, once we calculate that Q value, we can then determine our delta H, because Q is equal to the opposite sign version of delta H. And once we get our delta H, we can then determine a molar enthalpy for the reaction by simply taking that delta H and then dividing it by the number of moles of compound that reacted, okay, where we have kilojoules on top and of course moles on the bottom, which would give us a molar enthalpy measured in kilojoules per mole. And finally, for a good calorimetric setup, you need to have insulation. You need insulation. And this is because you want the energy transfer only occurs between the system and the H2O surroundings. And what this slide talks about, this slide mainly talks about the way we can communicate whether a chemical system is endothermic or exothermic. This slide is all about communication. So let's take a look at the endothermic side of this table. For an endothermic side, we can label an endothermic reaction with a molar enthalpy. All right, and we can see here that our molar enthalpy in this case is positive. Okay, it is a positive molar enthalpy. We can take that enthalpy change and place it next to the chemical reaction. Okay, and you can see once again the delta H value is positive. We can also place an energy term in a balanced chemical equation. So we could see here, look at where the energy term is. Endothermic reaction. We put the energy term on the left side, which goes with the reactants. This is what we would see for an endothermic reaction. We can also show a chemical potential energy diagram. What you should notice is that from reactants to products, we see an overall increase in potential energy. Okay, so because of this overall increase in potential energy, this is consistent with an endothermic reaction. Okay, well, what about the exothermic side? Well, for our delta H value, so our molar enthalpy value, it's negative for an exothermic reaction. We can also take that enthalpy value and place it next to the balanced chemical equation. Once again, notice how it's negative here. We can also take that amount of energy and place it in the balanced chemical reaction. If you notice where the energy is, in this case, it is now on the right side. So here for an exothermic reaction, what we see is we see the energy term on the right side. Right, and this is the product side. So for an exothermic reaction, the energy is a product. We can also do a chemical potential energy diagram. Notice going from reactants to products, what we see is we see a decrease in potential energy. So we see an overall decrease. In potential energy. All right, and that's consistent with an exothermic reaction. Now, first thing to note is that given how much energy is either going to be taken in by the chemical reaction or released by the chemical reaction, we have to remember that whatever energy term is stated, remember here, notice how these are molar enthalpies. So the energy values that are stated, these particular energy values go also, being able to communicate these sorts of things effectively, this is really important for your exam. You might see about around 6 questions just on the communication of an endothermic reaction versus an exothermic reaction. So this is where I like to say you got to be careful, knowing that the energy amounts go with whatever the mole amounts stated in the balancing coefficients are. Okay, so here's where I want to make this additional note first of all, pay attention to the units in the exam question. Also, pay attention to the balancing coefficients in the chemical reaction. So for example, let's say if we showed this chemical reaction, let's say if we were to show the combustion of butane, or like we saw in the previous example, methylpropane. Remember, they're isomers of each other. But in this case, I'm just going to show, for example, C4H10. Okay, so C4H10 gas would react with O2. And let's say this is a complete combustion, so what it's going to form is going to form CO2 gas and water gas as well. Now this is an exothermic reaction, so we would place the energy term on the right side. Okay, let's say it's 3.42 times 10 to the 3 kilojoules. Okay, notice how I'm giving it in kilojoules. This is where it kind of goes with what I was saying, is that you want to pay attention to the units in the chemical reaction. Let's say we balance the chemical equation like this. So here in this case, I'm going to put a 6.5 next to the O2. Here there's going to be a 4, and here there's going to be a 5. Hopefully it's easy to see that these balancing coefficients go with 1 mole of butane reacting. Okay, this value, given the way the balancing coefficients are, this value is associated with 1 mole. Let's say if I was to change the balancing coefficients as such, let's say if we double all the balancing coefficients, make this a 2, make this a 13, make this an 8, and make this a 10. If this here is the energy amount that goes with 1 mole, what's going to happen is that if I double all the balancing coefficients, the energy associated with this chemical reaction is going to double because all the balancing coefficients doubled. Okay, actually let me do this in a different color. I'll go back to the blue. This energy amount is going to double. And the reason why is because this here, this is associated with 2 moles. Okay, it's associated with 2 moles because we doubled the balancing coefficients. All right, so these are important things to remember. Always pay attention to the units that you're given in the question. And don't forget that if you do state an energy amount associated with a chemical reaction, it's going to go with the balancing coefficients of that chemical reaction, mole amounts. These are just illustrations to remind us that in an endothermic reaction, what happens is that the surroundings are cooled as the chemical system absorbs energy. Okay, we can see that we have an increase in potential energy from reactants to products in an endothermic reaction. But what happens is that thermal energy has to be taken from the surroundings in order to increase the potential energy of the chemical system in an endothermic reaction. In an exothermic reaction, there is a decrease in potential energy from reactants to products. Right? And this happens because the surroundings are now warmed as the chemical system releases energy. So now that we've gone through how to perform calorimetry calculations and also the ways we can communicate endothermic reactions and also exothermic reactions and how molar enthalpy values work with quantities given in the balanced chemical equation, or coefficients, or the coefficients I should say, we can now try a diploma style example. These next two questions, question 25 and 26, which you find in the back of the booklet, serve as a nice little summary. We have both a numerical response and also a multiple choice question. And we're going to use this information up at the top here in order to determine our answers. Okay, so if you want, go ahead and pause this recording, try this question out on your own, and then resume the recording when you want to see how the solutions are arrived at. With this question, we have ourselves a balanced chemical equation with the balancing coefficients that you see here, and we also have a delta H value for the chemical reaction. In the first question, in question 25, they want to know what mass of methanol, or what is the mass of methanol that burns to produce an enthalpy change of negative 9.00 times 10 to the 4 kilojoules in kilograms. Remember that I told you before that you always have to pay attention to the units in the question. All right, first things first. We have ourselves a delta H value that's associated with the chemical reaction given their balancing coefficients. What we should notice is that this delta H naught value is associated with 2 moles of methanol, okay, CH3OH. 2 moles of that. That is important to note. Now what we can first do, because we know that this is associated with 2 moles of methanol, we can set up a comparative ratio that allows us to determine how many moles of methanol would release this amount of energy. We know that 2 moles goes with negative 1,275.8 kilojoules. This is going to be equal to an unknown number of moles that would go with negative 9.00 times 10 to the 4 kilojoules. Now solving for x ought to be simple here. X in this case is going to equal 2 times that value times negative 9.00 times 10 to the 4 over our negative 1275.8. Now I'm just going to punch these numbers into my calculator, and what we get for the number of moles is 141.0879. I'll say 088. Okay, this is how many moles. And that's some extra sig figs. That ought to be sensible enough. We don't have to go overboard with the decimals. Okay, now that we have that number of moles, using the molar mass of methanol, and I have to state that when calculating the molar mass, make sure you use the atomic mass values that are given in the periodic table in your data booklet. Otherwise, you're not going to get the correct answer. So make sure you use these numbers. So the molar mass of methanol is going to be 12.01. That's, the molar mass or the atomic mass. The atomic mass or molar mass of carbon, there's only one of them. Plus, we have 4 hydrogens, so it's going to be 4 times 1.01 plus a single oxygen, which is 16.00, and this is equal to 32.05 grams per mole. Right, now that we have the molar mass, we can easily determine the mass, and don't forget that when we determine the mass using those two numbers that we have, we are going to get a result in grams. So I simply take the mole amount and I multiply it by molar mass. Right, and it's easy to see here that the mole units are going to cancel, leaving behind a result in grams. What we're going to get is 4,521 grams. Once again, pay attention to units. We want an answer in kilograms. If I divide this by 1,000 and round it to the correct number of significant digits, it should be 4.52 kilograms. And so that's the answer, 4.52 kilograms. And you can see, based on what I was talking about, if you look at the numerical answer that we get, and if we think about the way we're going to fill out our bubble sheet, there are 4 spaces. A bubble for the 4, for the decimal, for the 5, and also for the 2. Okay, so what about this last question? Well, this one's a little bit more hardcore calorimetry. We want to determine the amount of methanol that must be burned to raise the temperature of 250 grams of water from 20 degrees Celsius to 35 degrees Celsius. Just like before, what we're going to do is we're going to arrange our data values under surroundings and a system heading. Okay, so we have 250 grams of water. This is a mass of H2O. Remember what I said before, we want our mass of H2O in kilograms, so this is going to be 0.2500 kilograms. This is an initial temperature, this is a final temperature. We can easily calculate our delta T, 35.0 degrees Celsius minus 20.0 degrees Celsius. What do we get? We get 15.0 degrees Celsius. And of course, we have our specific heat capacity of water, 4.19 kilojoules per kilogram degrees Celsius. Under the system heading, we are looking for an amount of methanol. If we look at the answer options, they're all given in moles, so really it's going to be helpful if we determine the number of moles of HCl based on how much energy is released. Okay, but nonetheless, hopefully it's easy to see that what we're going to determine is we're going to determine a Q from the information that we have. Once again, when marking up your exam, you don't need to write down the units as long as you know your units are good. Okay, so what we get here is positive 15.7125 kilojoules. Okay, we get a result in kilojoules there. We also know that the delta H for this scenario, okay, and it's a delta H for combustion, is going to be the negative version of this. So it's negative 15.7125 kilojoules. Okay, so here's the thing. We know that this many kilojoules goes with this many moles. Once again, we could set up a comparative ratio. We know that 2 moles over negative 1275.8 kilojoules. That's going to be equal to an unknown mole amount. This is what we're trying to determine, over negative 15.7125 kilojoules. Our X is simply going to equal this. And that's going to equal about 2.46 times 10 to the minus 2 moles. And there's our answer, answer C. Your exam might ask you a question or two about either photosynthesis or cellular respiration. Here, let's start off with photosynthesis. Now, the sun is a major source of stored chemical energy on Earth. In fact, actually, the sun it's the source of energy for all chemical processes on Earth. So let me just write that out here. Now, photosynthesis, here are the different ways that we can communicate photosynthesis. Remember, photosynthesis is a chemical reaction that involves the reaction between carbon dioxide and water to form glucose and oxygen. Important thing to note is that photosynthesis is an endothermic reaction. It's an endothermic reaction. If you notice here that we have the energy term on the left side of the chemical equation. Also note the balancing coefficients that we see in front of each entity. And an important thing when understanding what's going on with the photosynthesis process or with any chemical reaction with an energy term in it, you must always be careful with ratios. Okay, it's endothermic because we see that energy term on the left. Also note that on this potential energy diagram, we see an overall increase in potential energy from reactants to products.